Differentiation of exponential functions with constant base, $x. Hello everyone. Let's begin today's lesson on the differentiation of exponential functions with a constant base. To start, let's recall what we have already covered. In our previous lessons, we learned how to differentiate the natural exponential function e to the power of x, and we found that its derivative is uniquely simple, as it is simply e to the power of x. However, in many mathematical problems and real-world scenarios, we don't always work with the natural base, e. We frequently encounter exponential functions with a different positive constant base, which we will represent as a, where a is greater than 0. Common examples of this would be functions such as 2 to the power of x or 5 to the power of x. In this subsection, we are going to explore how to derive the specific derivative formula for these functions, and, subsequently, how to apply that formula to solve practical problems. Derivation using logarithmic differentiation. Now that we have established why we need to differentiate functions with a constant base other than e, let's look at how we actually derive the formula. The most intuitive approach to find the derivative of y equals a to the power of x is by using a technique called logarithmic differentiation. The primary advantage of this method is that it transforms the exponent into a product, which makes the differentiation process much more straightforward. Let's walk through the step-by-step process together. First, we start with our function, y equals a to the power of x. To begin the transformation, we take the natural logarithm of both sides. This gives us the natural log of y equals the natural log of a to the power of x. Next, we apply the logarithm power rule. As you may recall, the log of a base raised to a power is equal to that power multiplied by the log of the base. Using this property, we can rewrite our equation as the natural log of y equals x times the natural log of a. It is important to keep in mind that since a is a constant, the natural log of a is also just a constant value. Now, we differentiate both sides of the equation with respect to x on the left side. Because we are differentiating the log of a function, we must apply the chain rule, which results in 1 over y times the derivative of y with respect to x on the right side. We are differentiating x multiplied by the constant natural log of a, which simply gives us the natural log of a times 1. To isolate the derivative, we multiply both sides of the equation by y. This simplifies our expression to the derivative of y with respect to x equals y times the natural log of a. Finally, we substitute the original value of y back into the equation. Since we defined y as a to the power of x at the start, we replace y to get the derivative of y with respect to x equals a to the power of x times the natural log of a. This brings us to our final formula. The derivative of a to the power of x with respect to x is equal to a to the power of x times the natural log of a. While this method is very intuitive, there is another way to derive this using the base e and the chain rule, which we will explore in the next slide. Alternative method, using the base e dollar and chain rule. Now that we have explored the first method of derivation, let's look at an alternative approach. We can also derive this result by rewriting the constant base, a, in terms of the natural base, e. Let's go through this step by step. First, we need to rewrite the base. Recall from your logarithm properties that any positive number, a, can be written as e raised to the power of the natural log of a. Therefore, if we replace the base in our function, a raised to the power of x becomes e raised to the power of the natural log of a, all raised to the power of x. By applying the power rule of exponents, we can simplify this to e raised to the power of x times the natural log of a. Second, we apply the chain rule. We know that the derivative of e raised to the power of a function of x is equal to e raised to that same function, multiplied by the derivative of that function. In this specific case, our function in the exponent is x times the natural log of a. Since the natural log of a is simply a constant value, the derivative of x times the natural log of a, with respect to x, is just the natural log of a. Third, we combine these results. The derivative of a raised to the power of x is the same as the derivative of e raised to the power of x times the natural log of a, applying the chain rule we just discussed. This gives us e raised to the power of x times the natural log of a, multiplied by the natural log of a. Finally, we simplify the expression. Since we already established in the first step that e raised to the power of x times the natural log of a is equivalent to a raised to the power of x, we can substitute it back. This brings us to our final formula. The derivative of a raised to the power of x is a raised to the power of x times the natural log of a. As you can see, both methods lead us to the same conclusion. Now that we have a solid understanding of where this formula comes from, let's move on to the next slide to see how we can apply this to a real-world population growth scenario. Real-world application example. Now that we have derived the general formula using two different methods, let us see how to apply this knowledge to a real-world scenario. Please look at the slide titled Real-World Application Example. We will be examining a scenario involving population growth. In biology, the growth of certain bacteria populations can be modeled by an exponential function. Suppose the population, which we will call p, at any given time t, measured in hours, is given by the function p of t equals p0 times 2 to the power of t in this context. P0 represents the initial population at the starting time. Our goal is to determine the rate of change of the population at any time t. Let us walk through the step-by-step solution. First, we must identify the function we need to differentiate. We are looking for the derivative of p with respect to t for the function p of t equals p0 times 2 to the power of t. Second, we apply the constant multiple rule. Since p0 is a constant, it remains unchanged during differentiation. Therefore, we only need to differentiate the exponential part, which is 2 to the power of t. This gives us the derivative of p with respect to t equals p0 times the derivative of 2 to the power of t with respect to t. Third, we apply the exponential derivative formula that we established in the previous slides. Recall that the derivative of a to the power of x is a to the power of x times the natural log of a in this specific problem. Our base is 2, and our variable x is t. Thus, the derivative of 2 to the power of t is 2 to the power of t times the natural log of 2. Finally, we combine these parts for the final result. The derivative of p with respect to t equals p0 times 2 to the power of t times the natural log of 2. This resulting expression represents the instantaneous growth rate of the bacteria population at any time t. This example demonstrates how the theoretical formula we derived is used in practice. In the following slides, we will summarize the key takeaways and discuss some common mistakes to ensure you apply this rule correctly. Key takeaways. Now that we have explored two different methods of derivation, let us summarize the key takeaways from this section. First, the most important point to remember is that the derivative of an exponential function with a constant base, a, is the function itself multiplied by the natural logarithm of that base. To put this into a formula, the derivative of a to the power of x with respect to x is equal to a to the power of x times the natural log of a. It is also helpful to see how this connects to our previous knowledge. This formula is actually a generalization of the derivative of the natural exponential function, e to the power of x. If we substitute the constant, with the base, e, the derivative of e to the power of x becomes e to the power of x times the natural log of e. Since the natural log of e is equal to 1, the expression simplifies back to just e to the power of x, which perfectly aligns with what we learned in earlier lessons. Finally, reflect on the process we used in the second slide. Logarithmic differentiation is a powerful tool in your mathematical toolkit because it allows you to transform a complex exponentiation into a simple multiplication, making the differentiation process much more straightforward. Now that we have mastered the formula and its derivation, let us move to the final slide to discuss some common mistakes you should avoid when applying these rules. Common mistakes to avoid. Now that we have explored the derivation and a real-world application of this formula, let us conclude by discussing some common pitfalls to ensure you avoid these mistakes in your assignments and exams. First, be very careful not to confuse the power rule with the exponential rule. A very frequent error is attempting to apply the power rule, which states that the derivative of x to the power of n is n times x to the power of n minus 1 to exponential functions. For example, if you were to say that the derivative of 2 to the power of x is x times 2 to the power of x minus 1, that would be incorrect. Please remember that the power rule is only applicable when you have a variable base and a constant exponent. In our current lesson, we are dealing with a constant base and a variable exponent. Therefore, as we established in the previous slides, the correct derivative of 2 to the power of x is 2 to the power of x multiplied by the natural log of 2. Secondly, students often forget to include the natural log of a term. While it is common to remember to keep the original function, a to the power of x, it is easy to overlook the multiplier. Always remind yourself that unless the base is the natural constant e, this scaling factor, the natural log of a must be present in your final result. Finally, let us address a point regarding notation. It is crucial that you use the natural logarithm, which is log base e, rather than the common logarithm, which is log base 10. In the field of calculus, the notation log almost always refers to the natural logarithm unless specified otherwise. Using base 10 will lead to an incorrect result, so always ensure you are working with the natural log.